done, enter your score into your Mimeo vote and then take out your math equilibrium worksheet homework from yesterday. So we're starting here with predicting shifts and entering in our grades in Mimeo. If you're done, you may put it back. Yep. Keep your quiz. That's fine. I just need your answer into your Mimeo vote, please.
Will the final review be due Monday?
Yes. Yeah, it'll be due on Monday.
Okay.
5:15. Today is May 15th. Better. 4 out of 5. 1, 2, 3, 4, 5. We had 5. We're getting better. We're not there yet. We have a test tomorrow over equilibrium. Yeah. And rate. Remember how we talked about rate at the beginning of this unit? We talked about how we can speed up the rate, like how fast things react. We looked at the surface area. We did those demos, catalyst, surface area, stirring, heating. We did all of those. So that's still part of this unit. And then the second half is what does it mean? Like, so we continue to go back to the equilibrium. How do we describe equilibrium?
Month for sure. All right, let's try this. Try this one more time, okay? We're getting better, but we still are. I think we just need to see more examples, work through the logic of what we're doing, and by doing that, we'll become more confident. And every time that you see a new or unique situation, you'll be able to address it a little bit better. So let's look at the equation. So, and I'm going to draw sticks to help me out. So Chloe, the first thing I do is identify what does not participate in the reaction. So does copper oxide participate in the reaction? No. So I cross this out. How about hydrogen gas? And energy? And copper liquid? No. Good. And then water vapor? Yes. All right. So the first thing I did was cross out the things that cannot participate. The second thing I do is I ask myself how many gas particles are in this reaction. So Macy, on the left side, how many relative gas particles do I have? 1. Thank you. And on the right side, how many relative gas particles do I have? 1. All right. So there is no preferred side. They are the same. If I were to change the volume or the pressure of the system, there is no shifting that's going to happen with respect to the gases. So let's look at the first question. It says decrease the volume. All right, so Steph, I look at the equation. It's a 1 and a 1. Will there be a shift based off of this? So no shift, no change. And it feels awkward to say that. Sometimes you're just like, okay, that doesn't feel right. But it is. There's no preferred side, so there's no shift. All right, I add copper. So I find copper, and I observe that copper is a liquid. So Ivan, will adding copper make a difference? Okay. No, it is as concentrated as it can get. So there will be no shift and no change. If I remove water vapor, all right, so Arlene, water vapor is over here, water as a gas, water vapor. If I remove it, take away, shift. So what's the saying? There you go, take away, shift towards. So it's on the right. If I take it away, we will shift to the right to replace it. So take away, shift towards. Now what's going to happen Megan, what's going to happen to the concentration of H2 if equilibrium shifts to the right? Am I going to use it up as a reactant, or is it being made as a product? If equilibrium shifts to the right, we have now made H2 a reactant. And it'll decrease. I'm going to use it up. So it will decrease. What's going to happen to the concentration of H2O? That will increase because I'm making it now. Okay. What if I decrease the concentration of CuO? Jarrett, what will happen?
I have
No shift. Why is it no shift? Because it's a solid. All right. No shift. It's not in the equilibrium expression. It is out of the equation. And if I cool the reaction, all right, Carson Schwartz, I cool the reaction. We will. Which side's energy on? Left or right? Left. If I cool it, am I adding it or taking it away? All right, if I take away on the left, equilibrium shifts towards it, so we shift to the left. If I shift to the left, Kenley, what happens to the concentration of H2? Increases. All right. Guess what? There's another one. All right, one more time. We're going to do this one more time tomorrow before you take your test. All right, but so there's a couple of things we're doing here. The first is we're asking what can be in equilibrium. Then we're talking about how many gas particles are there. And then when we introduce these different factors that can influence equilibrium, we ask ourselves what direction will equilibrium shift because of that change, and what happens to the concentration of a species in that solution. Okay, so keep that. Boom, keep it. Put it in your binder. And it is the 15th, 515. I literally just started writing February on my paper. I don't know why. Today is our last day of instruction for Unit 12. We've learned everything we needed to talk about. At this point, we are building our skill set with respect to equilibrium math. So you had two things to do for me last night. Number one was to complete the equilibrium math homework. So in your packet, we started off doing equilibrium expressions. Expressions of equilibrium are these statements here where we identify what in this equation is at equilibrium, and we compare the concentration of the products versus the concentration of the reactants, and we identify their rate of change, this K value, and that mathematically tells me the relationship of equilibrium. Which am I making more of? So K tells us things based off of how it compares to the number 1. If K is greater than 1, then we can make statements about what we have more of. Do we have more products or reactants? And then if K is less than 1, it tells us if we have more products or reactants. So turn and talk to your table partner. What does K tell us? If K is greater than 1, we have more. If K, oh, you're here. Okay. Not here. There is a video lecture from class yesterday. Actually linked.
It looks like you thought that too. Thanks.
That's not what I thought. That's what I chose to do.
That's actually great.
It seemed like it was a long time ago.
Yeah,
Like yesterday.
I remember I like go home and do work, and I look at some of the stuff
Sometimes when I go home to do homework, I just go home to do homework.
it's just not do.
Sound good?
I've heard things like Trailer Park Boys and eating.
Alright, give that a shot.
I don't play football really anymore.
Okay,
You still?
so we said that K is the mathematical relationship. This is a model. Models are really good at telling us certain things about a system. In this case, the K value model tells me about the relationship between products created in equilibrium and reactants available at equilibrium. If K is greater than 1, Carson, if K k is greater than 1, what do I have more of in my solution? Products. Fantastic. Mathematically, if the number is greater than 1, then the numerator has to be bigger than the denominator. So I have more products, and the reaction at equilibrium favors this direction, forward direction. If the number is less than 1, then Justin, what do I have more of at equilibrium? Reactants. Yeah, the bottom number was bigger, therefore I have to have more reactants. At equilibrium, the reverse reaction is favored, and I have more of whatever is served. Okay. How we wrote this was arbitrary. Someone just decided that this is the direction we would write it. If we were to write it in the opposite direction, our k value would change because the numbers would invert. You following me? So just write the k value based off of the way that the equation has been presented to you, and don't worry about like why was it written that way. Well, someone decided, and that's just the direction we went. Equilibrium. The subscripts on the k stand for different things. Ka means the equilibrium dissociation of an acid. How much of the acid is dissociating? Kb is how much of the base is dissociating. Kw is how much of the water is dissociating. Keq is any reaction at equilibrium. Or you can literally just write K, and you would know that that is a constant for a reaction. Better? Yeah. All right. Let's put some problems up on the board. The work for these was in Schoology, so let's do. You know what? Let's just solve. Out. 5, 6, 7, 8. And put this down. And let's turn and talk to our table partners. And I'm going to have Mackenzie, Jarrett, Carson M, and Arlene. You're my 4. Come on up and solve these problems. Otherwise, you're comparing your work to your table partners. If for some crazy reason you're not done, now is the time to do it. You have to write the KEQ equation in letter form. Solve the equation in letter form.
Oh. I have a question on when you got to here.
Yeah, well, K equals, and then you just divide this. So it's 1.1 times 2 divided by point. Yeah, it's by itself. So,
Alright, then we're solving for x squared. So x squared and
Oh, so you, like,
1.8 times 10 to the 33rd can do this little
couldn't you
crisscross
just multiply that together?
equal signs because they're
multiply
diagonal
that together.
Multiply those together, divide, and then
Alright, so
you
you
just
get x
divide
squared equals
that
14.5
by that.
Yeah.
Okay.
divided by 1.8 times 10 to the 33rd. And then we do the square root of both sides. So, how do we type it? We do it in 2 steps. First, we do it with the side of the square root, and then we do the square root of the side. So it's 14.5 squared divided by 1.888 and then you square root that number. So it goes your square root.
You get,
Square root.
yeah.
7.2.
Mm-hmm.
3.4.
0.0724.